Line structures. So, by the way, I'll tell you on your homeworks, if you're asked to draw the structure of a molecule, a lot of times it does not specify whether you draw it in the condensed form or the line structure form or the full Lewis structure. For me, anything is acceptable as long as the structure is correct, okay? So if you like drawing line structures better than condensed structures or vice versa, either way is okay on your homework. So you can draw using any of these formats, okay? So line structure, again, we saw these on the tables though with the functional groups. This is probably the most simplified and the quickest way to draw molecules. You just have to make sure you get it right. So it's a way to simplify structures. The carbon-carbon bonds are drawn as lines, all right? And we often angle them, okay? The way you see here, not in a straight line. It would make no sense if we draw it like this. We couldn't tell where one carbon bond begins and where one ends if it's a straight line. So we draw them in these jointed lines, kind of zigzag lines. So the end of a line or the joining of two or more lines is a carbon, all right? Atoms other than carbon or hydrogen are shown. So what atoms could those be? Oxygen, nitrogen, sulfur, any of your halogens. Okay, we do draw those in. But lone pairs are omitted for clarity. But you still need to know how many lone pairs each thing would have. Okay, because carbon always has 4 bonds, any bond not shown is assumed to be to hydrogen. Okay, so for example, we have these examples right here. CH3, CH2, CH2, CH3. That would match up with this line structure. Here's the CH3, here's the CH2, here's the CH2, here's the CH3. Okay, so any dead end is a CH3 group. All right, so we have a branched alkane here. Here's the branched CH3 group right there. And that would match up with the branched butane group that you see there, okay? So let's say, what if we had oxygen in it? So if you see something like this, this is you would have oxygen drawn in, or you could even have nitrogen drawn in. And a lot of times they will write the number of hydrogens with the nitrogen, but that's only for nitrogen, okay? There'll be a lot of practice problems that I have in the textbook and remember, in the back of the chapter, textbook problems, any of the evens, you can look up the actual answers and check yourself on the evens. So that's why on the syllabus, the ones I recommend you to practice are just the even number ones. So let's actually put this into practice now. I want you to draw a line structure. This is ibuprofen, by the way. Try to draw the line structure for this. This looks complicated, right? And drawing out all the carbon-hydrogen bonds would just be nuts. So it's very simple, though, if we draw this out in line structure. So I want you to start over here. The place to start is on the left side. I like to draw these left to right. So I've got a CH3 group bonded to this CH group right here. So I'm just going to angle that just like that. And then I have a branched CH3 group coming up. So I'm going to branch upwards. That's going to be my CH3 group. Then I have this carbon bonded to another CH2 group. So I'm going to branch that down. And then we have this whole ring structure here, okay? So this carbon that we've just drawn is bonded to this carbon, which is part of a ring. Okay, so I'm going to branch this up, and then I'm going to begin my ring. It's a 6-member carbon ring. So if this is carbon 1, and that's carbon 1, I'm going to say carbon 2, 3, 4, 5, and 6. Now I'm going to draw all these carbons in, and I'll go back and add the double bonds. So I'm going to draw up to carbon 2. I'm going to draw a hexagon, essentially. Okay. Hold your applause, please, on my beautiful hexagon. All right, now I need to draw the double bonds in. I have a double bond up top. I have a double bond right here on the side and another double bond here on the side. So again, this looks like the bare bones of this, and it is. We're not drawing in all the hydrogens, so don't worry about all the H's. We're just notifying where the carbons are. So this carbon 4 here, which is the same as right here, this is carbon 4, is bonded to this carbon, this CH group. So I'm going to draw a straight line out to that CH group, and then I'm going to branch it down. That's this CH group, branch down. And then all that I have left, look, what functional group is this? Anybody? We got a functional group here.
Alcohol.
Close, Cameron, that's part of it, but the alcohol is bonded to a carbonyl carbon. So when you see that OH group bonded to a carbonyl carbon, it's a little more complex than just an alcohol. Anybody remember?
I don't think I can pronounce it correctly, but it's the carbonyl acid, the carboxyl acid.
Carboxylic acid. Yep.
Carboxylic acid. Okay.
You're going to get it, Madison. Carboxylic acid. So now we're going to draw the carboxylic acid. So I'm going to branch this over to that carbon. So this carbon right here that at the dead end is the same as that one right there. Now I'm going to double bond it to an oxygen. We don't write the lone pairs in. And then I'm going to branch it down to my OH group. So that is the line structure. Okay. Now it's not as beautiful as what you'll see in the textbooks, but that is all the right connections are there. Any questions on how we just did that? If you want more practice on this, there's a few problems here I recommend you do practice on. All right. Okay, so that's two different formats or two ways, condensed structures, line structures, that you can draw molecules for your homeworks, for the exams, whatever you're more comfortable with. Now we're going to talk about shape, okay? This is going to be key, especially in identifying isomers and conformers and things like that. You have to know with alkanes, okay? So we're not talking about alkenes or any other functional group. We're just talking about alkanes here. Straight or branch chain alkanes, they do not have fixed shapes. Now, the bonds can't break and rearrange, but here's what we mean. They can have multiple what we call conformations. Multiple conformations. What is a conformation? It's just the 3D arrangement. It's just actually how it would exist three-dimensionally in space. Okay? Why do they have multiple conformations? Here's the key part of this. Because there's rotation around the carbon-carbon bonds. It's maybe the most important part of this statement. Carbon-carbon bonds can twist. They can rotate without breaking, okay? Now, this is important too. It affects the energy of the molecule. When things twist, sometimes they can be wadded up together. And when you find groups, branch groups especially, that are like make the molecule really compact, those are less stable. They're higher energy. When things are more spread out and relaxed in a molecule, they're lower energy and they're more stable that way. So I'll point that out in a second. So to give you the definition of what we call a conformer, we're going to have to differentiate between conformers and isomers. These are molecular structures with identical connections. So same molecular structure, but different spatial arrangement. So all the atoms are connected the same. They would have the exact same Lewis structure. Okay, remember, isomers don't have the same Lewis structure. They have the same molecular formula, different Lewis structures. Conformers have the same exact Lewis structure. Everything's connected the same way. They're just twisted different. Okay, so for example, we have different conformations right here of the exact same molecule. So we've got these two carbons that have a methyl group, a CH3 group bonded off of each, and then we got hydrogens also bonded off these carbons. So each of these middle carbons, these internal carbons, have two hydrogens and a CH3 group branched off of them. Can y'all see that? So these CH3 groups can be twisted different ways. So in A here, we have this CH3 group twisted down and this CH3 group twisted kind of up. Okay, that's the down and that's the up. And everything's kind of spread out nicely. On B though, what do you notice? Both of the CH3 groups are pointing upwards. Okay, so we twisted, it's as though we twisted this carbon-carbon bond right here. That's not easy to see, but if we twisted this, we would twist that CH3 group up. But notice that a dashed line, so look, this is a dashed line right here. That means that CH3 group is pointing backwards out of the plane, and this one would be pointing forwards. So this one would be pointing backwards, and this other CH3 would be pointing forwards. A straight line or a wedge line is pointing forwards. A dashed line is pointing backwards. So they're still a little bit spaced out because of that, just spatially. And then we can have even another conformation, C over here, where they're both pointing forwards. And this is the most crowded form, okay? When those methyl groups are both twisted up and they're both in the same plane. Okay, so this would have the highest energy. This one would have the lowest energy. It would be the most stable. And the other one would be the least stable, okay? Because it's just the most crowded. So this would be the most crowded. Does that make sense? Okay. So let's review a little bit. How are isomers and conformers different? This is where the vocabulary can get confusing. Isomers, these are molecules with the same molecular formula, but different connections. They would have different Lewis structures. So we call that a structural formula. Lewis structure, structural formula, same thing. Conformers, these are the molecules, same molecular formula, and they have identical connections. They would have identical Lewis structures. Okay, that's how an isomer is different from a conformer. So I want you to look at these molecules. I'm going to poll question I'm going to launch. A, B, and C. You see two different condensed structures. But are these molecules, if you look closely, if you twist things around in your mind, okay, are they actually identical molecules? Remember, something that's branched, if it's at the end of a molecule, could actually be straightened out. So for example, this right here, this actually could just be branched off that way instead. You could just twist it down. Does that make sense? In your mind, you might have to mentally do some of these things. Okay, so I want you to tell me, A, looking at these two things, are the following pairs of compounds the same? If they're the same, we call those conformers. If they have actually different connectivities between the atoms, they're isomers, or if they don't even have the same structural formula, like one has a nitrogen and one doesn't, or they got different numbers of carbons, we would say they're unrelated, not even close. Okay, so I'm going to launch this poll, and just give me your best guess. Okay. All right, I'll give you another 30, 45 seconds here. We're going to go over them together. So if you're like, I don't even know, we'll look at these. Okay. Just throw your guess in if you're not sure. All right, we're almost there. There we go. In poll. Share results. So it doesn't say who voted what, and that doesn't matter. But you can see on A, most people said conformers. Okay. So conformers means that they are basically the same thing, same connectivity between all the atoms. Okay. Just different 3D arrangements in space. And that is true here. Okay. So if we took this CH3 group and just swiveled it down, okay, it's still bonded to this CH2. Then we would have a straight chain, just like that one, of 1, 2, 3, 4, 5 carbon atoms in that chain, okay, just the way we do over here. And we would have a CH3 group branched off of carbon 2. Do y'all see that? It does not matter if it's branched up or down. I said that earlier. So don't be confused that this CH3 up here is branched up and this one is branched down. It's the same. You could easily flip the molecule 180 degrees and get the same spatial arrangement. So these are identical, all right? Same molecule, the atoms are all connected this way, so these are conformers. Any questions on that? Okay, on B, most everybody said isomers. So let's look at this. Isomers means they just have a different connectivity amongst the atoms. So the easiest way to look at that is if we just took this group and kind of put it in the straight chain, what we would end up with is CH3. I'm trying to make it, see if I can make it look like the other one. CH, CH2, CH2, CH3, and then we would just have this CH3 group branch. So if we just made it a straight chain, I see that I got 1, 2, 3, 4 in that straight chain, but you could you'll find out later, you could also count it like this. You could also say I got 1, 2, 3, 4, 5 in my straight chain, and then I've got a methyl group branched off carbon 3. But here the methyl group, the CH3 group, is branched off carbon 2. So these are definitely, that might be confusing what I just said. We haven't learned how to name things yet, but these are definitely isomers, because no matter how you bend it or rotate it, you don't get the exact same spatial arrangement. Okay, does that make sense? So that's why these are isomers. So we found out that the molecules could be overlaid and be exact mirror images, like they mirror each other exactly. But these, no matter how you straighten it out or try to make it work, you can't line these up exactly, so they're isomers. Okay, what do y'all think about C? C, most everybody said unrelated. And that is true. Even if you look at the number of hydrogens, we got 3, 4, 5, 6, 7, 8 hydrogens here. And here we only have 3, 4, 5, 6 hydrogens. So that's not even the same molecule. You don't even have the same number of atoms, at least when it comes to the hydrogens. So this is definitely, you got a carbon oxygen double bond here. This is a carbon oxygen. This is a single bond here. Okay, now anybody remember what functional group that is on C? Carbon, oxygen to carbon. Is it an ether or an ester?
Ether.
It's ether. Mm-hmm. Is that Cameron? Good job. Okay, so these are unrelated. And this, what would the functional group be on this other one? What is this right here? Anybody recognize it? You got a carbonyl carbon. It's the simplest kind of carbonyl functional group. You got a hydrogen branched off it. So this is a ether over here. This will be an aldehyde. Okay. Anyways, that's not part of the problem, but I want you guys to be familiar with recognizing functional groups. Okay, we're going to get to naming alkanes. So we have a system. It's called the IUPAC system. You'll see that a lot. International Units of Pure and Applied, or International Union of Pure and Applied Chemistry is what that stands for. But that's, you don't have to memorize that. But that's the system that all these rules for naming come from. So if you hate naming, and we're going to spend a lot of time learning the rules of naming, then you can hate IUPAC for that, not me. So if we're going to name alkanes, so we're just talking about alkanes. We're not even talking about alkenes yet. That's like a whole nother chapter. Alkanes. Remember, you can have straight chain alkanes or branched chain alkanes. Straight chain alkanes are the simplest things to name. Okay, so we've got a table here for these. Straight chain alkanes are named by counting the number of carbon atoms and then adding the family suffix, ane. Okay, so you'll find out, depending on the number of carbons, as you have more and more and more, we have particular words associated with that number. So if you have 1 carbon, and then it's just got 4 hydrogens, the word for that is, we say that's a methyl group, methane. Here it's methane. If you have, so like 1 carbon, we'll get to this too, branched off of something, we call that a methyl group. The root word here is meth, okay? Meth is the word we associate with 1 carbon, all right? So here we're adding ane on the end because it's an alkane. You just have carbon, hydrogen, single bonds. So we put that together, it's methane. If we have 2 carbons, the root word we associate with 2 carbons is eth. Okay, so it goes meth for 1, then eth for 2. So it's, if you add the family suffix, it's ethane. We have all carbon single bonds, carbon, hydrogen, single bonds. So methane, then ethane. As you grow longer and longer, 3 carbons is prop, P-R-O-P, prop. All right, so methane, ethane, propane. 4 carbons is bute. So if it's an alkane, it's butane. 5 carbons, 5, 6, 7, 8, 9, and 10 correspond more with words you probably heard or prefixes you probably heard. So pent, Like a pentagon has 5 sides, so pentane, and then hexane, heptane, octane, nonane, and decane for a molecule that's a straight 10 carbon chain, okay? So you need to know how to name. Now, you're not going to see beyond 10 carbons. I'm not going to have you name that. But up to 10, you need to know how to name straight chain alkanes, okay? All right, that's straight chain. Branch chain's more complicated. Okay, so if we have branched alkanes, here is kind of the root formula. You're going to have a prefix, then you're going to have the parent name, and then you're going to have the suffix. Now, if it's an alkane, that suffix is always ane, right? So what do the prefix and the parent part of the name tell us? Okay, the prefix portion is going to include numbers and commas and dashes. These are all telling us where the substituents are located. What the heck is a substituent? Well, substituents are groups such as a CH3 group or a CH2 CH3 group that could be branched off of the main chain, okay? These are called alkyl groups, okay? Alkyl groups. So if you have just a CH3 group, we call that a methyl group. Okay, notice the meth root word because it's just a 1 carbon group. So essentially, you just take the naming for the straight chain, you look at how many carbons are in your substituent group, and you just change the ending to YL. You just call it a methyl group, an ethyl group, a propyl group, a butyl group, pentyl group. It could get large. You're really not going to see more than a butyl group, okay, like a substituent that has 4 carbons in it. But that's how you name them. They're called alkyl groups. So alkyl groups are derived from parent alkane. So that's what I just walked through. If you have methane and you take off this hydrogen, now you have a CH3 group, and we call that a methyl group. Same thing for the ethyl group. If you just remove one of the hydrogens, it doesn't matter which one. They're all perimeter terminal hydrogens. So that's what I'm saying here. It doesn't matter which hydrogen is removed. For now, it doesn't matter. It will matter in just a second. All right. For larger substituents that have 3 or 4 carbons, it does matter which hydrogen you take off. And I know this is technical. This is organic chemistry for you. All right. So that's the prefix part. The parent part of the name, that's just telling us how many carbons are in the longest continuous chain. So we'll count that and we'll name it according to that. That'll be the parent root word, and then we'll just throw on the name ending, the suffix, so that we know what family it belongs to. Right now, we're just naming alkanes, so the name ending will always be ane. All right, so why does it matter which hydrogen you take off for 3 and 4 carbon substituent groups? Well, let's look at this. Let's look at propane. So propane is a 3 carbon straight chain alkane. Anybody head swimming yet? CH3, CH2, CH3. So I've got this drawn out. Well, this is actually a figure from your book. You see all the carbons and hydrogens. If you take off a hydrogen in red, okay, this is an end carbon, or you could call it a terminal carbon. You're going to get a group that looks like this. Doesn't matter which one you take off from the end, okay? And so you get a group that looks like that, 3 carbons in a row. That would be a propyl group, okay? Propyl group. That's a straight chain propyl group. But if you take off an inside carbon, one of these blue ones, now you're attaching this group, but you're attaching it through the middle carbon to whatever other straight chain or molecule you're bonding it to. So now you have what we call an iso, because it's an isomer, isopropyl group, okay? Isopropyl group, all right? So this is what we call a branched chain, because we're branching to the right and to the left. This is all straight chain, but when you attach it from the middle carbon, now you have 2 methyl groups branched off that middle carbon. So we call that an isopropyl group. So if you have a 3 carbon substituent, so for example, if I have 1, 2, 3, 4, 5, I have a 5 carbon straight chain, and I branch off of this carbon right here. Boom, boom, boom. Okay. This right here, well, this would actually be a terrible example. Let's say I have a really long chain of carbons and I branch off at 3. I'm branching off. I would call this a propyl group. Does that make sense? But if I branch it and I attach it through the middle carbon, I have an isopropyl group. You're going to run into the same thing for 4-carbon substituent groups. So let's look at butane. Butane is even more complicated. If you have a 4-carbon straight chain alkane, that's butane. If we start pulling hydrogens off and then attaching that butane group to another molecule, we have to be able to name that substituent group. So there's different ways to name it depending on which hydrogen you pull off of which carbon, okay? So here are the 4 options. I'm just gonna tell them to you and then we're gonna dissect them. You could have a butyl group. That's if you take off an end hydrogen. Again, it could be from either end cap, okay? That's a butyl group. You could have a sec butyl group. I'll explain that in a second. You could have an isobutyl group. That one's branched. Or you could have a tert butyl group. That one is also branched. So if you have butane and you start ripping hydrogens off and connecting that butane to another molecule, you can end up with 4 different kinds of groups. Butyl, sec butyl, isobutyl, or tert butyl. Now, what does that mean? Why do we have this little sec or tert butyl? 2 of these, by the way, these first 2 are straight chains. You can see that. These other 2 are the branch chains. Sec and tert, these are prefix words that indicate what kind of substituent group it is, okay? So when we, and you'll see this when we get to alcohols, especially a lot too, we have to have a way to classify carbons, okay? So if we zoom in on this right down here, this is a figure from your textbook. If you have a carbon that is bonded to one other group that's not hydrogen. So for example, 3 of these bonds here, 1, 2, 3, are to hydrogen, but one of the bonds is to some other atom. It could be carbon, it could be nitrogen, oxygen, just any other atom that's not hydrogen. We call that a primary carbon. It has one other, if we pretend that it's carbon, one other carbon attached, okay? If a carbon has 2 other carbons attached, so R here is representing a linkage to another carbon. So we are just going to focus on carbon right now, not bonded to nitrogen or oxygen or anything. So if you've got a carbon bonded to 2 other carbons, then that is a secondary carbon. If it's bonded to 3 other carbons, that's a tertiary carbon. If this carbon has no hydrogens attached, it's bonded to all 4 carbons, we call it a quaternary carbon. And we use these little signals here. I want you to really just focus on these. A 1 with a degree sign, or a 2 or 3, 4 with a degree sign. That stands for primary, secondary, tertiary, or quaternary. Okay, so that is where this sec and tert is coming from. Look at the carbon, the one that has the red line attached to it. This carbon is bonded to that carbon. If you draw the Lewis structure out, you can see that, and it's bonded to that carbon. So that corresponds to this right here, a carbon that has 2 hydrogens attached, okay? Well, one of them has been taken off. That's why it's a second. We've removed one of the hydrogens from this carbon so that we can attach it to another molecule. Okay, it's now becoming a substituent group. But we call it a sec butyl because it's bonded to 2 other carbons. All right, so it's a secondary carbon there that you're attaching the butane group through. All right, isobutyl is kind of has its own name. We don't call this a tertiary butyl because it's very similar to isopropyl. Okay, so we're actually, the way this would look if you draw it as a line structure, we have this carbon here, and then it's bonded to another carbon, and then it's got these methyl groups. All right, so it kind of looks like that, but it's branched. It looks very much like isopropyl in a sense. That's why we call it isobutyl. But tert butyl here, we have like an isobutyl group, but instead of bonding it through a terminal carbon, we're actually bonding it through that central carbon there. So that's where we get tert butyl, because this carbon in the middle is bonded to 1, 2, 3 carbons. Okay, so it's a tertiary carbon. So that's what we call it, tert butyl. We're bonding it through, this is now a substituent group that's bonded to another molecule through a tertiary carbon. Okay, so that's a lot, and this is just a very small part of organic chemistry. Okay, these are just substituent groups. Questions on this? Some of this may just be all jumbled up in your head, and when you start actually writing these out and seeing them on paper, they'll help a little bit more. But that's just naming straight chain alkanes and then naming groups. Let's get to the overall rules. So these are like the 4 dominant rules for how to name alkanes, period, whether they're branch chain or straight chain. We've already looked at straight chain, but especially when you get to branch chain. Okay. All right. Step number 1, you're going to name the main chain. Okay, so we're going to find the longest continuous chain. You may have to turn corners to name the longest continuous chain. It might not all be straight. Okay, and you're going to name it according to the number of carbons in that chain. So you can go up to that table. What table am I talking about? You can go to this table right here if you're confused on how to name it. If the longest continuous chain has 7 carbons in it, it's a heptane. All right. Step number 2. You're going to number the carbon atoms in the main chain and be sure to begin at the end near the first branch point. Okay, so this is a branched alkane. You're going to start from the end nearest the first branch point. So for example, if we're going to number all the carbons here, we want the longest continuous chain possible. I could number it like this: 1, 2, 3, 4. I can't go to the left or down because if I actually, you see that the longest continuous chain is if I go up and over. I got 6 carbons in the longest continuous chain here. But I can't number it this way because these branch points, we're not following step 2. We want to number the carbons in the main chain so that we begin at the end near the first branch point. So we got to number them in the reverse order. If that makes sense. We got to say this is carbon 1, this is carbon 2, and this is carbon 3. Now these branch points are occurring at carbon 3, not carbon 4. Make sense? So 3, we say that's carbon 4, carbon 5, and carbon 6. All right, so that's step number 2. Step number 3 is identify what your substituents are. Substituents are the branched groups, okay? And you're going to number each of those. You number them according to their point of attachment to the main chain. So if I'm zooming back in on this, we would say, okay, this little methyl group right here is branched off at carbon 3. And this one, this is another methyl group. It's also branched off at carbon 3. Okay? So keep that in your pocket. We'll use it in just a second. If there are 2 substituents on the same carbon, and that's what we have on this molecule, assign the same number to both. So we're going to say that's a methyl group that's branched at carbon 3, and that's a methyl group branched at carbon 3. Each attached group has to have its own number. All right, even if it's the same number. Now we're going to write out the name of this. Okay, so here's some helpful formatting tips when we're writing the name out. Use hyphens or dashes to separate numbers and prefixes. I'm gonna walk you through all this in a second. Use commas to separate numbers. If 2 or more different substituent groups are present, cite them in alphabetical order. So for example, ethyl would come before methyl because E comes before N. Okay. A sec-butyl would come after a tert-butyl, right? So on and so then T, tert-butyl will come after sec-butyl, okay? So you're looking at, so isobutyl would come before tert-butyl and things like that. If 2 or more identical groups are present, then you're going to use prefixes such as di, tri, or tetra. But you don't pay attention to the prefixes when you're alphabetizing everything. Okay, this is super confusing. Let's actually try to write out the name of this. Here's what I know. My longest continuous chain has how many carbons in it?
6.
6. So what are we going to name the parent name of this? The parent name is what? How do we name a 6-carbon alkane?
Is it hexane?
Yes, Cameron, hexane, okay? So I'm going to write the name hexane out here. But now we have to account for the fact that we have these 2 substituent methyl groups, and they're both branched off the same carbon, carbon number 3. So I've got to write out, remember it said that you've got to have, every substituent has to have its own number. So I got to write 3, 3. Remember it said to use commas to separate numbers. So 3, 3. And it says if you have 2 or more identical groups, and we do, both of these substituent groups, why don't I actually box them in blue, a different color? Maybe that'll make it easier to see. Okay, both of these substituent groups are identical. They're both methyl groups. Okay, so I have 3, 3, and it says use hyphens to separate numbers and prefixes. So I'm going to use a hyphen here to separate 3, 3 dimethyl. And then I can scoot hexane over. It's all one word. Why did I say dimethyl?
Because there's 2 methanes attached to the 3rd carbon.
Right, and that's this right here. If 2 or more identical groups use prefixes such as di, tri, or tetra. So I got 2 identical groups bonded to the same carbon, 3, 3, and then I use a dash to separate my numbers from my prefixes. It's dimethylhexane. Okay? This, you will get more comfortable with this. It's a lot of rules, okay? And it'll kind of become like a little puzzle. We're going to do some more practice, but it's a lot at first to take in. I want to name this next one. So first, this one's kind of nice to look at, right? It's going to be pretty easy to number the main chain, the longest continuous chain. So let's do that. 1, I'm going to start numbering here and not on the other end. Why? Because I want to give my first branch point the lowest number possible. If I start numbering from the other end, my first branch point will have a 3, but here my first branch point is at a 2. So that's carbon number 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7. Okay, now we got 7 carbons, so what kind of compound is this? It's all carbon-hydrogen single bonds. We got no double bonds, no functional groups, crazy here. It's a hexane, right? Or sorry, it's an alkane. But what name denotes 7 carbons?
Hepta.
Heptane. Thank you, Cameron. So it'll be heptane. So I'm going to try to write this underneath. So we have the parent name down, but now we have to account for all the substituents, and we're going to write this part out front. This is where we got to do the alphabetizing, write the numbers, the commas, and the dashes. So I see that on carbon 2, I have a methyl group. And then on carbon 5, I have another methyl group. So what do y'all think we should write? They're identical groups. We got 2 methyls. So probably like we did up here, we had 2 identical methyls. We're going to have to say dimethyl. But the numbers should be different.
Would it be 2,5 dash dimethylheptane?
Yes, Madison. 2, 5, because that's where they branch off carbon 2 and 5. Then we're going to do a dash to separate the numbers and the prefixes. Dimethyl heptane, sorry. Is it starting to click a little bit?
Is dimethylheptane one word, or is there a space between dimethyl and heptane?
It's all one word. Yep. Okay, now we have a line structure. This looks a little more complicated. I want you to try to name it yourself first. So you need to count this. Remember, you got to count from the side. That gives your first branch point the lowest number. And you got to try to find the longest continuous chain of carbons. Maggie, you got it? Sorry, I think you're muted.
I said, I think I didn't want to write the wrong thing down and then have to erase it.
Anybody want to share maybe what they got? It's totally okay if you're wrong. This is just part of learning. Well, first thing we're going to do is get the numbering right. So what did y'all get for how many carbons in the longest continuous chain?
Octane.
8. Okay, so I'm going to number it this way. 1, this looks like the longest one to me. 3, 4, 5, 6, 7, 8. I agree with Cameron, octane. So I'm going to go ahead and write that out here. Okay, now I got to look at what substituents I have. It's a little different when you're looking at it in the line structure form versus the condensed structure form. But here's what I notice. On carbon 3, I got a methyl group. On carbon 4, I have another methyl group. What is this group up here? Anybody been able to name that substituent? So we got a carbon, and then we got a CH3 and a CH3. So we have a 3-carbon substituent. So the root word of that substituent is going to be prop. But what kind of, is it just propyl? Or is it 2 options? We got propyl or isopropyl. What do y'all think? So remember when we talked about 3-carbon substituents, that was right here. Did we remove a hydrogen from an N carbon, a terminal carbon, or from the internal carbon to connect this propyl group to our molecule?
Internal, so it'd be isopropyl.
Correct. That's right. We took the hydrogen off of this carbon right here, and that's the internal carbon. So this is an isopropyl group. Does that make sense? Do not think you're behind if you're like, I'm having a hard time recognizing this. This is how organic chemistry is. It takes lots of practice. So we have an isopropyl group coming off of carbon number 4. So looking at the first letter between isopropyl and methyl, how do we need to alphabetize this? Isopropyl first, right? So it's going to be 4. And we're going to do a dash to separate or a hyphen to separate the numbers and the prefixes. So 4 isopropyl. Then we're going to do another dash because now we got to account for the 2 methyl groups. If we got 2 identical groups, it's dimethyl. And we got to use numbers to indicate what carbons they're branched off of. So it should be 3, 4 dash dimethyl octane. So you should have 4 isopropyl. So this tells me off of carbon 4, I got an isopropyl substituent, if I read this. Then off of carbon 3 and carbon 4, I have methyl groups branched off of those. And my longest chain here is the octane. And it's all carbon-hydrogen single bonds. So it's that's why it's an alkane with the root name ending suffix of -ane. Okay. How do y'all feel? You feel accomplished? For more practice, and these are on your, it's on the lecture schedule as well. Practice this, okay? You can check your answers. These are all evens. Okay, wow, we have like an hour left to do and we're not even done. Really quick, I'm gonna move through, that's kind of the hardest part. So these next couple of slides, I'm going to move through a little bit faster pace. Again, slow me down if you need to, but we need to finish this so we can wrap up and move on to our lab activity, okay? Properties of alkanes. So you guys remember what the words polar and nonpolar means. If you don't, review some of this stuff, chapter 8, section 2. Alkanes are nonpolar, okay? So we're going to classify these. I think you have more text on this slide. I forgot to take it off or cover it up. But I want you to try to classify this as true, false, true, false. I'm going to launch a poll. Just for the first 2, actually. Alkanes can hydrogen bond, true or false? Alkanes are soluble in water. What would you predict based on what you know? These are just alkanes, just composed of carbon-hydrogen bonds and carbon-carbon bonds. Both of these bonds are nonpolar bonds. All right, we got 6 of the 7 votes. There we go, in poll. Okay, here's what we got. We got mixed reviews, so I'm glad we're talking about this. Hydrogen bonding only works, if you remember what hydrogen bonding is, It only works if you have an oxygen and or a positively polarized hydrogen, okay? You need lone pairs on an oxygen, nitrogen, and fluorine, and then a positively polarized hydrogen. None of the hydrogens in alkanes are positively polarized, so this is false. They cannot hydrogen bond. The strongest type of intermolecular force, hold on, for alkanes, let me erase this. They can only experience weak London dispersion intermolecular forces, okay? You remember the London dispersion or van der Waals, and then dipole-dipole interactions and hydrogen bonding? Hydrogen bonding is the strongest. So alkanes can only experience London dispersion. Those are the weakest. Soluble in water, this is also false. Water is very polar. Okay, so if alkanes are nonpolar, they're not, like dissolves like. Remember that phrase? They cannot dissolve in water. Okay, the last one, I'll just tell you, this is true. Okay, they're held together. I'm going to delete these other things. You can see this other information. They're insoluble in polar solvents such as water, but they are soluble in non-polar organic solvents. Okay, and then they have very low melting and boiling points. Okay, so low, in fact, that the first four simplest alkanes, the methane, propane, ethane, and butane, these are gases at room temperature. Okay, here's a little table to indicate this. Based on the number, I'm on the eraser. Based on the number of carbons, so this would be methane, ethane, propane, butane, so on and so forth. You can see what the relative melting and boiling points are, but melting points are in blue, boiling points are in red. So the longer the chain goes, the more carbons you add onto it, the more energy and heat it takes to melt or boil those compounds, okay? You don't have to memorize any of these exact numbers, but do know the trend. So if I said, for example, I have something here. If I said, C2H6 versus C8H18, if I said which one's going to have a higher melting or boiling point, for example, on exam, I would want you to be able to tell me based on this trend here, okay? Does that make sense? That's the kind of question I would ask you about this. Obviously, this one's going to take more energy. It's going to have a higher melting and boiling point because you got a lot larger molecule here and a lot more London dispersion forces holding those molecules together. All right, that's properties, reactions of alkanes. This actually should be familiar to you. Oh, stop sharing that. The only type of reaction we're going to talk about with alkanes is combustion. And you guys, I know if you took me for 1402, I definitely talk about combustion reactions. You should maybe recognize what a combustion reaction is. Ignore this statement up here. I don't have any curved arrows on this slide. You might see curved arrows in examples in your textbook. Just remember any arrow indicating movements of electrons represents 2 electrons, okay? Combustion. This is the reaction of an alkane with oxygen. Okay, so an alkane is a hydrocarbon, carbon-hydrogen only, so it could be so many different things. It could be methane, ethane, propane, butane, anything. Reacting with oxygen, the complete combustion of alkane always yields 2 things, carbon dioxide and water. And it is always exothermic. You guys remember that word, exothermic? Negative delta H, exothermic. Meaning it releases energy. Okay, if you watch a combustion reaction, you're going to see fire or an explosion, right? And you can obviously tell, common sense tells you heat is being released. What else did I have here moving forward? Okay, I don't have anything written above and below the arrow, but in organic chemistry, what we're going to run into a lot of is we may write things like heat, okay, or spark. Okay, for a combustion reaction, it takes some sort of spark or initial ignition to start the reaction. And those things are written usually above and below the arrows. That's all this is saying down here. If you have a catalyst or a particular solvent that it needs, those will be written above and below the arrow. Okay. So, all right. Any questions? That's combustion. Always yields CO2 and water. That's the only reaction I want you to recognize from alkanes. Now we're going to talk about cycloalkanes. I think 1, 2, 3 slides and we're done. All right, so cycloalkanes. These are carbon hydrogen molecules, single bonds, that are in a ring structure, okay? And first thing I wanted to know is that cycloalkanes, they're important biologically, okay? Many drugs, this is the structure of morphine, have ring structures within them, okay? Additionally, they share similar properties to straight chain alkanes. So everything we said earlier about they're not soluble in water, they're nonpolar, they have low melting points and boiling points. This is also true for cycloalkanes, okay? They're soluble in organic nonpolar solvents, but not in stuff like water. And then they have restricted rotation. So we're saying for the branched or the straight alkanes that you can rotate them all kinds of ways. Cycloalkanes, you cannot, okay, because they're within this ring structure. So here's some of the ways you can look at how the naming goes. If you have 3 carbons, 1, 2, 3, you know that the root word is propane. We call it cyclopropane, okay? If you have a 4-carbon ring, we call that cyclobutane. 5-carbon cyclopentane. 6-carbon cyclohexane, so on and so forth, okay? You just add the word cyclo to the front of it. All right, and then now what happens though if you have substituent groups attached to your cycloalkane? Well, what happens is we just have to name them with the numbers and the dashes, just like we did before. So if you have one group, notice we have this one methyl group attached to our cyclohexane here. We would just call this methyl cyclohexane. And this is also showing you the line structures for how to draw it. This is like the condensed structure. And then these are just the line structures over here. In a ring, it can be, I don't know if you're going to think it's a little trickier or easier to name or number the carbons. But if you have one substituent group, you're going to start numbering. You're going to say, that's my carbon number 1, okay? Because you don't have any other reference point, okay? We don't have any, like, you don't have to figure out which end you have to number from like you would on a straight or a branched chain alkane. You're just going to call that first substituent carbon number 1. Okay, this is all 2-way intersections here represent CH2 groups. This right here would be a CH group. And a line at the end, this would be a CH3 group. Okay, but that's part of the line structure stuff we talked about. All right, here are the specific rules for naming cycloalkanes. Number 1, use the cycloalkane name as the parent. Those are like the names we talked about, like right up here: propane, cyclobutane, pentane, hexane. If there is only one substituted group, it's not even necessary to number the other groups or to number the carbons, period. That's why here you just see that it's not one methyl cyclohexane. You just call it methyl cyclohexane. It doesn't matter if the 1 is there or not because you only have one substituent. But the moment you have more than one substituent, okay, when there is more than one attached group, you have to identify and number them. Okay, so start numbering at the group that has alphabetical priority. What does that mean? Well, let's look at this example. We have, what is this group? Can somebody tell me what that substituent, how we would name it? These are both alkyl groups. Is it a methyl group, ethyl group, propyl, isopropyl? What kind have I underlined right here in blue?
Would it be ethyl?
That's right, this is an ethyl group. How do we know that? 2 carbons, okay? So this is an ethyl group. And this one right here, what's the one in green?
Methyl?
Yep, this is a methyl group. So which one has alphabetical priority?
Ethyl group.
The ethyl group. So we're going to name that one first. So we're going to call, all that it's saying is this is going to be carbon 1. Now we're going to start numbering to give the next substituent the lowest number. So should I number clockwise or counterclockwise? I want to give my methyl group the lowest number possible.
Counterclockwise?
Counterclockwise, that's right. So what that means is I'm just going to number this. This is going to be carbon 2. So my methyl group is going to be branched off carbon 3. So the way I'm going to write all this out, when it all comes together, this, by the way, I better keep numbering so I know how many carbons are in my ring total. There are 6 carbons here. So what's my parent root name for this? Cyclo what?
Hexane?
Cyclohexane. hex denotes a 6 carbon, well, cyclohex represents 6 carbons in a ring, hexane, because it's all carbon-carbon single bonds. So cyclohexane. So if we're going to number this now, put all the substituent info in front, what we'd have is 1-ethyl. Then we do a dash, and we have 3-methyl. So 1-ethyl, 3-methyl cyclohexane.
Why did you go counterclockwise again?
Because I wanted to give this methyl group the lowest number possible. If I counted in a clockwise manner, this would have a 5 on it instead of a 3. And we want to give it the lowest number possible, Cameron. Great question. Hey guys, pause real quick. I need to handle something for just a second. Okay, I'm back. Sorry. When you got a sick kid, stuff comes up. Okay. All right, so questions on what we just did. We're going to try to name these next 2 cycloalkanes, and then that's it for the lecture for today. We'll have about an hour to do our lab assignment, which should be more than enough time. So I want you to try to name these cycloalkanes right here. What do y'all think for the first one? Oh,
I can't see it.
You can't
Yeah,
see
I
my
can't see
screen, can you? Sorry. There we go.
Would it be 1-ethyl, 4-methyl cyclohexane?
Okay. That's what Madison says. She said 1-ethyl, 4-methyl, cyclohexane. Okay. Anybody agree or disagree?
I agree.
I
Robin?
agree.
All agree? Okay. So we have the same groups here as we do over here. They're just spaced out a little differently around the ring. So this is definitely an ethyl group, and this is a methyl group. And we start numbering that as a 1. Ethyl gets the 1 because it's got alphabetical priority. It doesn't matter if I number this as 2, 3, or 4, or if I go the other way. You're going to find out that the 4 lands on the methyl group substituent either way. And there's 6 carbons total in the ring, so it is a cyclohexane. So 1-ethyl, 4-methyl cyclohexane. And then, so yeah, that's the correct name for that one. Let's do one more. This one's not a cyclohexane. Anybody recognize this is going to be a cyclo what?
Pentane.
Cyclopentane. So I'll go ahead and write that. Now I have to identify what substituents I have. You guys should recognize this is an ethyl group. But what kind of substituent do I have over here on the right? It looks like this if you draw the line structure for them. It's a 3 carbon, 1, and then a CH3, and then a CH3. It's a 3 carbon substituent. So it's either propyl or isopropyl. What do y'all think? take a snack or a pouch and give it to him right now. I think propyl or isopropyl.
Isopropyl.
Is isopropyl, okay? If it was propyl, it would look, the substituent would look like this: CH2, CH2, CH3. But this looks a little bit different. We are branching off of the center carbon, the internal carbon. So that is why this is an isopropyl group, okay? So now we have to figure out which one has alphabetical priority, ethyl or isopropyl. And you should say ethyl, right? So we're gonna number this carbon 1. It's important to figure out that alphabetical priority thing so you know where to start numbering. So that's gonna be number 1. I'm gonna number this in a clockwise fashion because if I do, that means my isopropyl group is carbon 3 instead of carbon 4. So we put this all together now. We're gonna get 1 ethyl, 3 isopropyl, cyclopentane. Okay. So this is a lot of info for one day. And I do have a practice slide down here. I would actually like you to try this on your own. And then if you want to check your answers with me, feel free. But I've just got a bunch of compounds here. The different functional groups are circled, and I want to see if you can, use this as practice to label those. But we're going to switch gears here. We have just under an hour left to do our actual lab. Any questions on lecture material?
Does there need to be a dash after the 3 and before the isopropyl?
Oh, yes, Madison. Thank you. I forgot that.
Just making sure. Thank you.
There should be a dash there for sure. No, those things matter.
Why did you start the other way and go counter or go clockwise?
Maggie, because I wanted to give this second group, my isopropyl group, the lowest possible number here. Okay. So if I would have numbered the other way, like 1, 2, 3, this would have had a 4. It'd be 4 isopropyl. But what it tells us to do, it says proceed around the ring in the direction that gives the second substituent the lowest possible number. Okay. So that's why you got to look at, all right, do I need to number clockwise or counterclockwise? Which way is going to give my second substituent the lowest possible number?
And you started with ethyl because it starts with an E?
Yes, because that one has alphabetical priority. Ethyl goes first alphabetically, so that's why we give it a 1. Or start numbering with the letter that's higher up in the alphabet, if that makes sense. And so that would be 3, carbon 4, and carbon 5. Okay. That's lecture for the day. All great questions. If you realize you have another question later, shoot me an email. I am going to have to take my son to the doctor today at 1:50 because he's running fever right now. So instead of a